Hello friends, welcome to YouTube channel Electronic. In this video, we will learn Thevenin's theorem. In any electric circuit, if you want to find current and voltage in any element, we can find by using Kirchhoff's voltage law and Kirchhoff's current law. But if you want to find the voltage and current across these two terminals for the 20 different values of this resistor value R3, this may be possible by using Kirchhoff's voltage law and current law. But it will take a lot of time to find it. Many times it is very important to see the behavior of the electric circuit for the different kinds of loads. So in such cases, Thevenin's theorem is a quite useful technique. So by using Thevenin's theorem, we can replace the entire circuit across these two terminals X and Y by an equivalent voltage source in series with an equivalent resistance. And it doesn't matter how complex the network is. We can apply this Thevenin's theorem. Now in the equivalent circuit, this equivalent voltage is known as Thevenin's voltage and this equivalent resistance is known as Thevenin's resistance. So Thevenin's voltage is the voltage that we can find across the network after removing the load. Similarly, the Thevenin's equivalent resistance is the resistance that you find across these two terminals after removing all the independent sources and replacing them by their equivalent resistance. In case of ideal voltage source, it has zero internal resistance. So we can replace ideal voltage source with a short circuit. Similarly, in case of ideal current source, it has infinite parallel internal resistance. So we can replace ideal current source with an open circuit. So to find a Thevenin's equivalent resistance, we will replace voltage source by a short circuit and a current source by an open circuit. One more thing is that how complex the given circuit may be, we can apply Thevenin's theorem. It may contain independent sources, means output of these sources does not depend upon the voltage and current of any other part of the circuit, or the circuit also may contain dependent sources, which means the output is governed by a voltage or current in any other part of the circuit. Now there are three different cases to apply this Thevenin's theorem. The first case is that the circuit contains all the independent sources. The second case is that the circuit contains independent as well as the dependent sources. And the third case is that the circuit contains only dependent sources. We will discuss these three cases one by one. Let's start with the first case. The circuit contains all the independent sources. In this circuit, there are two independent voltage sources. Here we need to find out Thevenin's equivalent circuit across these two terminals X and Y. First, we will find Thevenin's equivalent voltage. To find this, first of all, let's remove this load resistor of 20 ohm. Now apply Kirchhoff's voltage law in this circuit. Let's assume that the current I is flowing like this. As per KVL, here we can write this applied voltage 10 volts equal to voltage drop across each component. So 10 volt equals to 10 ohms into I plus 10 ohms into I. Here this 20 volts is ideal voltage source. So it have zero series internal resistance. Hence we can write it as plus 20 volt. If you simplify this, 20I equals to minus 10. Therefore, I equals to minus 10 divided by 20. That equals to 0.5 ampere. Here, this negative sign indicates that the current is flowing in the opposite direction. Now, here the Thevenin's voltage is nothing but the voltage across these two terminals X and Y. That is nothing but voltage drop across this 10 ohm resistor. So, the voltage Vxy equals to applied voltage 10 volt minus the voltage drop across the other resistor, that is 10 into I. That equals to 10 minus 10 into current I minus 0.5 ampere. That is nothing but 10 minus into minus 5. So 10 plus 5, that equals to 15 volt. Therefore the Thevenin's voltage across these two terminals is 15 volts. So now let's find out the Thevenin's equivalent resistance. To find the Thevenin's equivalent resistance, resistance, we will turn off all the sources. Because of zero internal resistance of these two ideal voltage sources, they can be replaced with a short circuit. Now the equivalent circuit will look like this. That is nothing but two 10 ohm resistors are connected in parallel. So the Thevenin's equivalent resistance RTH equals to 10 ohms in parallel with 10 ohms. That equals to 5 ohms as the value of RTH. So now if we draw the Thevenin's equivalent circuit where we have found that VTH equals to 15 volts and RTH equals to 5 ohms. So the circuit will have Thevenin's voltage source of 15 volts in series with Thevenin's equivalent resistance of 5 ohms. Now let's connect the 20 ohm resistor across these two terminals X and Y, which we have removed earlier. Suppose if you want to find the voltage and current across these two terminals X and Y, then we can find it easily. In this way, we can find Thevenin's equivalent circuit for the circuit contains all the independent sources. Let's see the second case where the circuit contains both independent and dependent sources. So this is the circuit. First of all, we will find Thevenin's equivalent voltage across these two terminals X and Y. If you observe this circuit contains two nodes. This is the first node X and this is the second node. Let's denote it with Z. Here the voltage across this node X is nothing but VTH. So now if you see these two nodes, there is a voltage source between these two nodes. So we will consider this node as a super node and we can treat these two nodes as a single entity. So now let's apply Kirchhoff's current law at this super node. So we can write, let's observe this part. Here the current at this resistors is nothing but Vz by 2 kilo ohms plus Vz minus 5 by 2 kilo ohms. Now at this part of the circuit it is plus Vx by 1 kilo ohms and this Vx is nothing but VTH. So it is VTH by 1 kilo ohm. That equals to 0. Here if you see at this super node, we can write Vz minus Vx equals to 3 Vxy. That can be written as Vz minus VTH equals to 3 Vxy. Here this Vxy is nothing but VTH. So we can write this as Vz minus VTH equals to 3 VTH. Hence Vz equals to 4 VTH. So now we can insert this value Vz equals to 4 VTH in this equation. After inserting this value, we will get 4 VTH by 2 kilo ohms plus 4 VTH minus 5 by 2 kilo ohms plus VTH by 1 kilo ohms equals to 0. Let's simplify this. Here LCM is 2 kilo ohms. So 4 VTH plus 4 VTH minus 5 plus 2 VTH divided by 2 kilo ohm equals to 0. That equals to 10 VTH equals to 5. That means VTH equals to 5 by 10. That equals to 0.5 volts. So in this way we found Thevenin's voltage at 0.5 volts. Now let's see how to find Thevenin's resistance in this circuit where the circuit contains both independent and dependent sources. In this type of cases, just short the terminals X and Y where we want to find the equivalent resistance and find the short circuit current ISC through this terminal X and Y. So here RTH equals to VTH divided by ISC. If we short these two terminals X and Y, then this 1 kilo ohm resistor will also get shorted. Because of this short circuit, the voltage Vx equals to Vy. So the voltage across terminals X and Y equals to 0. Hence this dependent voltage source will also get short circuited. So if you see the equivalent circuit, it will looks like this. In this equivalent circuit, if you observe this 2 kilo ohm resistor will also get short circuited. So if you draw the equivalent circuit, the circuit will have 5 volt voltage source in series with a 2 kilo ohm resistor and hence the short circuit current ISC can be given as VTH divided by RTH. That equals to 5 volt divided by 2 kilo ohm. That equals to 2.5 milliampere. So the Thevenin's resistance can be given as RTH equals to VTH divided by ISC. Here we know that VTH equals to 0.5 volts and ISC equals to 2.5 milliampere. So RTH equals to 0.5 volt divided by 2.5 milliampere. So we will get the value of Thevenin's resistance as 200 ohms. So if we draw the Thevenin's equivalent circuit, it will looks like this. The circuit will have 0.5 volt voltage source in series with a 200 ohm resistor. So in this way we can find Thevenin's equivalent resistance where the circuit contains independent as well as dependent sources. Now let's discuss the third case where the circuit contains only dependent sources. In this type of cases, the value of Thevenin's equivalent voltage will be equals to 0 as it does not contain any independent sources. Now to find the Thevenin's equivalent resistance, we need to apply test voltage or current across its two terminals. Suppose if we are applying test current, then just find the voltage across this test current. After that, the Thevenin's equivalent resistance RTh can be found by the ratio of voltage and the value of the test current. So in this circuit, we will apply test current of 1 amperes across these two terminals X and Y. Here the first thing that we will see is I1 equals to minus 1 ampere. It is because according to Kirchhoff's current law, the algebraic sum of currents meeting at a common point is 0. Here I1 is flowing in opposite direction, so that at point X the sum of the currents is equals to 0. Let's assume that Vx is the voltage that is appearing across this current source. So if we observe this part of the circuit, the applied test current 1 ampere equals to the sum of the currents across these both resistors 4 ohms and 6 ohms. So 1 amp test current equals to Vx divided by 4 plus Vx divided by 6 minus 3i1. Here it is minus 3i1. It is because this 3i1 current flowing in opposite direction of the applied test current. Hence 1 ampere equals to Vx divided by 4 plus Vx minus 3x minus 1 divided by 6. Let's simplify this. 1 equals to Vx divided by 4 plus Vx plus 3 divided by 6. That equals to, here the LCM of 4 and 6 is 12. So 3Vx plus 2Vx plus 6 divided by 12. So 12 equals to 3Vx plus 2Vx plus 6. If this plus 6 goes left hand side, then 6 equals to 3Vx plus 2Vx, that equals to 5Vx. Hence Vx equals to 6 divided by 5, that equals to 1.2 volts. Now Thevenin's equivalent resistance equals to Vx divided by I. So RTh equals to 1.2 volt divided by 1 ampere, that equals to 1.2 ohms. So in this way, if circuit contains only dependent sources, then by applying a test voltage or current, we can find the Thevenin's equivalent resistance. So by using Thevenin's theorem, any linear and bilateral circuit can be converted into the equivalent voltage source in series with the equivalent resistance. This equivalent voltage source defined as Thevenin's voltage and this equivalent resistance defined as Thevenin's resistance. Let's briefly know about the Norton's theorem. According to Norton's theorem, we can replace any linear bilateral network by equivalent current source in parallel with the equivalent resistance across its two terminals, where this equivalent current source is known as Norton's current IN and this equivalent resistance is known as Norton's equivalent resistance RN. Here this Norton's theorem is exactly dual of Thevenin's theorem. So just by using source transformation, we can find Norton's equivalent circuit. That means this current IN is nothing but VTh divided by RTh, and this Norton's equivalent resistance is nothing but Thevenin's equivalent resistance. Hence any Thevenin's equivalent circuit can be converted into Norton's circuit by using source transformation. That's all about Thevenin's theorem. If you have learned from this video, please do mention them in the comment section below. Thanks for watching. If you like this video, please click the like button. Help others to learn by sharing this video. Please subscribe and turn on notifications for more such videos. Have a nice day.